Alrighty, so welcome back, and now we on part 2 of our excursion into these beautiful limit problems. So, waste no more time. Okay, so let's have a look at this one very quickly. Haha, limits at infinity, this is what we call asymptotic behavior. Interestingly enough, now have a look at this very carefully. You have 2x cubed plus 7 all over x cubed minus x squared plus x plus 7. So it's of the form p of x over q of x, correct? And they're polynomials. And if you notice very quickly, the highest power of x there is 3, and the highest power of x there is 3. Interestingly enough, so let's have a look at this. So we go equals to the limit as x tends to infinity. Now, if you just blindly substitute infinity there, you're going to get an infinity over infinity situation with a direct substitution, and this is what we call unpretty. So let's try to make this pretty by dividing top and bottom by x cubed. So if I do that, I'll have every term 2x cubed over x cubed plus 7 over x cubed, top and bottom x cubed over x cubed minus x squared over x cubed, plus x over x cubed plus 7 over x cubed. And you can see where this is going now. This is the limit. The top x cubed and x cubed, so there's going to be a 2, but you're still left with 7 over x cubed there. In the denominator, that doesn't go away, that's just 1, be careful. Minus 1 over x plus 1 over x squared plus 7, right neatly, plus 7 over x cubed. And as x tends to infinity, and the case, what is infinity? So infinity, very large number. So you notice that as x tends to infinity, this number is going to get 7 over a very, very large number. In fact, it's cubed, so this is going to tend to 0. This term is going to tend to 0. That term is going to tend to 0. That term is going to tend to 0. So your final answer is just going to be 2 over 1, which is 2. So look at the leading term. If you got this form for the limit, leading terms, x cubed in this case, x cubed in the denominator, divide the top and bottom by that leading term, and as x tends to infinity, you would end up with a nice, beautiful, cute constant, in this case 2. Okay, now have a look here. Similarly, test. If you just substitute minus infinity here, you'd notice that you got an infinity over infinity case. So it's got that form p of x all over q of x. Nice mangoish color, I like to call that. And also we look at the leading term here. So here we got x to the power 4. So tell us divide as x tends to minus infinity in this case. So you're going to get 9x to the power 4. You can do this in your mind. So that becomes x over x to the power 4. But sometimes it's always good to present as much as possible to the examiner. Always think the examiner as the most ignorant person that exists on the planet. So you need to provide detail. And then you notice that here, so there's a constant. The rest of these terms, that's going to go to 0, that's going to go to 0, that's going to go to 0, that's going to go to 0. Please check all of that. So your final answer is a bubbly 9 over 2. Very nice. Hope you follow that. Okay, so let's have a look at the next one. What is this? So direct substitution here, again, very unpretty. Very unpretty. And now you don't have leading terms because you use a fractional power x to the power half. But it tells me, let's make a plan. Let's try something here. This is 2x to the power half plus 1 over x to the minus 1, all over 3x minus 7. Now, if you put x tending to infinity, you notice here you're going to end up with infinity there, and you got infinity there. So it's still very unpretty. But it points to something else. So the limit as x tends to infinity, take a common denominator there, so this becomes 2x to the power 3 over 2 plus 1 all over 3x squared minus 7x. So you notice very carefully now, this is interesting. Do this slowly, by the way. At the top, you have an infinity, and at the bottom, you have infinity. But the leading term on top and bottom, you got 3 over 2, and you got a 2 there. So what if I divide top and bottom by x squared? What do I get? So that becomes the limit. Okay, x squared, I said, hey, watch this. So this becomes 2 over x to the power half plus 1 over x squared all over, now watch, 3 minus 7 over x. Each of these terms, this is going to go to 0. This is going to go to 0. That's going to go to 0. So the final answer there would be a lovely symmetric 0 as x tends to infinity. So have a look. You know, these problems, they come in varieties, flavors. So direct substitution, infinity over infinity, unpretty. Let's try to pretty that up. So in this case, we can't divide immediately top and bottom by the leading term. We have to make a plan, take a common denominator, simplify, and then divide by the highest power of x, and the answer is actually 0. Sweet. Okay, what have we here? Now watch this. It's 1 over x squared minus 4, but here, this is the thing we need to understand. What it's really saying is if I got minus 2, I'm approaching minus 2 from the right, which means all values greater than minus 2. Now be careful, you get thrown out because minus 3 is not greater than minus 2. No. But things like minus 1, oh my goodness, is this math or what? Minus 1, 0, minus half. They're all greater than minus 2. A direct substitution, minus 2 in there, gives you an unpretty number like 1 over 0. So how do we tidy this up? So if you have a look, watch this. I want to write this as the limit, 1 over. Now x squared minus 4, you already know is x minus 2 into x plus 2 as x approaches minus 2 plus. Now look at each of the factors. We know there's a situation here, but let's deal with the first term, x minus 2. X minus 2 for values of x greater than minus 2, like minus 1, 0, those sort of values here. All right, what do we have? So take a value like 0, 0 minus 2 is negative, minus 1 minus 2, negative. So this guy is going to be less than 0. So the first factor here is less than 0. It's negative. Now look at x plus 2. X plus 2. So if you look very carefully over here, you'd find that all values greater than minus 2, minus 1, 0. This one's going to be positive. So the product, one's negative, one's positive. So the product, x minus 2 into x plus 2, negative times positive, will be less than 0. So we know there's a hole, or what we call a singularity. That's a beautiful word there. At x equal to plus 2, because you put in minus 2, you're going to get a 0, you're dividing by 0. So what it tells me is this graph is going to dip to negative infinity. So this would be minus infinity. In fact, if I try to sketch this graph, have a look at this, and let's just see whether we actually understand this one. The graph would look something like this. Let's just try and put lots of information for you. And it's not necessary to actually draw the graphs. There's y, there's x. We notice there's an asymptote at x equal to 2, but there's also an asymptote at x equal to minus 2. There's a lemony color there, lemony. So this is, oh, you can hardly see that. That's minus 2, that's plus 2. Now try to look at the asymptotic behavior of this thing, all right? As x approaches minus 2 from the right, from the left of minus 2, you'll notice for all values less than minus 2, like minus 3, minus 4, minus 5, as such. So you're going to find that this graph is going to be creeping up, and this shoots off to plus infinity. All right. Now notice what happens at 2. If you're approaching x for all values greater than 2, take values like 3, 4, 5, substitute in there. 3, 4, 5, 6, 7. you'll notice the graph, as it creeps up to 2, it'll shoot up to infinity. You'll also notice that when x is 0 in the original function, the function takes on a value of -1/4, which is somewhere down here. But as we pointed out, look at what we had here. If you're approaching -2 from the right for all values greater than -2, the graph shoots down to -infinity, which basically means the graph does that. And it has to go there, and the same thing would happen as x approaches 2 to the left of 2. It'll go down to -infinity. So this graph, y equal to 1 over x squared minus 1, looks like what I've just drawn over there. You don't need to sketch this. This is the point. You can actually analyze it, but the real treat in this problem is to understand what we mean by x approaching -2 plus. That means x approaching -2 from the right of 2. That is, all values greater than -2. Okay, what we have here. Okay, x squared minus 3x plus 2 all over x cubed minus 4x, x approaching 1 plus. What does that mean? So there's 1, you're approaching 1 plus, which basically means you're approaching 1 from the right of 1, all values greater than 1. And as you get closer and closer to 1, let's just do a direct substitution. Direct substitution. What would you have in the numerator? You'd have 1 squared minus 3 into 1 plus 2 all over 1 cubed minus 4. So here we're going to get a 0 on the top, and the bottom we're going to get 0 over minus 3. What is that? 0 over minus 3. 0. Don't overthink it. Ooh, beautiful. Sine of ax over bx as x tends to 0. Now, when we see this, this should tell us that we need to start thinking sine x over x as x tends to 0 is what? It's 1. It would have been nice, instead of having sine ax over bx, it's nice if this was an a. So how do we do that? Well, it's pretty straightforward. So we go limit, watch this, 1 over b, sine of ax all over ax. Hey, where did the a come from? I put it there. So I'm going to multiply by a there, with that as x tends to 0. So this thing now looks like sine x over x, right? So this would be a over b. We can take that out because this is a constant. Sine of ax all over ax as x tends to 0. And that is going to be not 1. It's a over b times 1. This whole thing is 1. And so the answer is a over b. Ta-da! Done. Sweet. Simple. Dusted. Oh my goodness, what is this? This is brilliant, because now we're looking at what we call piecewise functions. All right. The notion of a limit, behavior of functions around that value x equal to a. It doesn't have to be at x equal to a, but around that value actually points to the concept of continuity. Are functions continuous? Do they have jumps? Do they have breaks? Or what we call discontinuities. Now watch this. This is a piecewise function. So it's basically split into parts. It behaves like a parabola, 1 plus x squared, for all negative values, including 0. Between 0 and 2, it's a linear function. It's a straight line. And for all values of x greater than 2, you notice that it's a parabola again, x squared minus 4x plus 4. So you can actually plot these different parts and link them up, and you get what we call a piecewise function. So the question, it says here, the limit of f of x as x tends to 0, but from the left of 0. From the left of 0 basically means the first portion of the graph applies, because it's less than 0. So you just stick in 0 in there. So the limit of f of x as x approaches 0 from the left of 0 is 1 plus 0 squared, which is 1. Think about that carefully. Okay, let's look at b. Here the limit of f of x as x approaches 2, but from the left of 2, from the inside of 2. Inside of 2 basically means if this is 2, we approaching from the left of 2, all values less than 2. So you'll basically look at the middle section of the function, which is 2 minus x. So substitute 2 in there, not minus 2, 2, and you get 2 minus 2 So that's going to give me 0. Now let's look at C. Please check that. All values limit f of x to the same function, but x greater than 2. X greater than 2. 2 plus. Doesn't mean plus 2. X tending to 2, but from the right of 2. Numbers like 2.1, 2.2, 2.3. So you look at the third leg of the function, which is x minus 2 all squared. Substitute 2 in there, 2 minus 2, and that's going to give me a 0. So finally, limit of f of x as x approaches 2. Now watch this, watch this. The limit of f of x as x approaches 2 minus is 0. Right? All values less than 2. The limit of f of x as x approaches 2 plus all values greater than 2 is 0. Right? So the left-hand side limit is equal to the right-hand side limit about the point x equal to 2. Hence, the limit of f of x as x approaches 2 is going to be what? Yes, it's going to be 0. Sweet. Simple. Go through that very slowly. Whoa! Okay, what's happening over here? Find the values of a and b that make f, there we go, continuous. So how can we smoothen up the function? So the function is broken up into 3 regions here, 1, 2, 3, x less than 2, between 2 and 3, and then x greater than or equal to 3. This problem was taken from one of my favorite textbooks, Calculus by Stewart. I got an old edition, the 6th edition, so I thought I'll make mention of beautiful book, excellent problems. Got me through university, and I thought I'll make special mention of it. And thank you for the existence of this book. So if we want to make this function continuous, so it tells me that the function, if I had to draw this function, I must be able to draw it without lifting my pen up. So it then tells me that if I look at 2, this is where the junction is. That's really cool. The junction, let's say 2. Then the limit from the left, the limit from the right must be equal. So basically, you're saying that the limit of f of x as x approaches 2 minus must equal to the limit of f of x as x approaches 2 plus, because that's the junction. That's the one. And then the second part is the second junction at 3. So we say that the limit f of x as x approaches 3 minus must equal to the limit of f of x as x approaches 3 plus. So what do we have here? So basically what we're saying is nothing more than taking x squared minus 4 over x minus 2. Now that's what we're going to do, right? We're going to do a direct substitution. And that must equal to, so we mesh them up, ax squared minus bx plus 3. But for x equals to 2. And then at the other junction, let's use this mangoey color, we must have ax squared minus bx plus 3 equals to 2x minus a plus b at x equal to 3. Now you notice what's going to happen. For the first one in red, if I put in values, x squared minus 4 over x minus 2, you notice the problem at 2, but if I factorize, it's x minus 2 at the top into x plus 2. So the left here is going to give me, so this whole red thing is going to give me 4 equals 2. And that's going to be 2 squared is 4a minus 2b plus 3. So this is going to be 4a minus 2b plus 3. That's equation 1. Mangoish color here, so we're going to get 9a, because I'm substituting 3 here, minus 3b plus 3 must equal to 6 minus a plus b. And then you can tidy this up quite nicely by saying 10a minus 4b equals to 6 minus 3, which is 3, and that's equation 2. So have a look at these two equations. I have 2 equations with 2 unknowns. I'll be able to solve them simultaneously, and bang, I get a and b. And when we put that into the original piecewise function, it ensures that the function is continuous about that junction 2 and 3. Awesome. Go through this slowly. Understand what you're doing. And I love math. Beautiful. Thank you for watching.